Hello everyone, my name is Rustam Azimov, and today my talk will be about algebraic path problems. In these problems we analyze graph, consider the different paths in this graph, and try to compute the properties of these paths using the different algebraic structures like semirings. Let's first start with some simple examples. Here, the well-known the shortest path problem when we have directed weighted graph, and we can associate with every path its weight just as sum of the weights of its arcs, and we here assume that the weight of the empty path is 0, and we can solve the different problems. For example, fixing some source vertices or destination vertices, and we can solve single shortest path problem, or all pairs shortest path problem, etc. And the direct solution for this is just to build a system of equations. For this we build adjacency matrix of this graph with adding additional artificial weights infinity. For the situations where here is we don't have any arcs, and such weights must not affect the shortest paths. And to solve, for example, the all pair shortest path problem, we must build the matrix X with elements the weights of the shortest path between each pair of vertices, and we can just use the fact that if we have some shortest path, then the path without first arc will be also a shortest, and build such system of equations where we first use the weights of first arcs in each path, and then recursively use the weights of rest of the paths. And for special variables where source and destination vertices are the same, we also must look at additional candidate for the shortest path. It is the empty path. So here we also check we compute the minimum of this expression and 0. And we want to somehow solve this system of equations, and for this example we can get the following solution with all the weights of shortest paths. And another example is computing the language accepted by a given finite state automaton. Here we have some source vertex, and some vertices are choose to be destination vertices. And on the edge we have sets of symbols from some finite alphabet sigma. Then we just can associate with every path the word just by concatenating the symbols on its arcs. And for the empty path, let's assume the word to be empty word, epsilon. And we just want to compute the set of words obtained by paths from one source vertex and all destination vertices. Here again we build a system of equations. We can initialize the matrix, adjacency matrix of graph representation of finite state automaton, and it will have as elements the set of labels on the corresponding arcs. And here we want to compute again the matrix X, but for example, we can solve the more general problem and compute such elements for all matrix X, and thus we solve this problem for all pairs of states I and J. We just consider all states as initial and all states as final states. And here we can build the following system of equations. We again just split our path into two parts. First is the first arc of this path and the rest of the path. And here we use the concatenation operation over the sets of words and union of the sets. And we describe two examples of path problems. In both cases, we show how we can build a set of equations using different operations. But it's worth to notice that not the case that every solution of these equations is a solution of the initial problem. For example, on previous slide, we can see that the set of all words sigma star is always a solution of the equations. And now let's talk about algebraic graph problems in general. We built two systems of equations, and they are very similar. They use two different operations. One is multiplication, and another is addition. Here we can generalize it and build the following system of equations. And here also we use the element which denotes the information about empty path. And in our two previous examples, in all pair shortest path problem, plus denotes minimum operator, multiplication denotes plus, and the information about empty path was just 0. And for the For the second example, we have the union operation, concatenation operation, and the language that contains only empty word. Now, behind these two operations, we have the algebraic structure semiring. Here we also can have the natural elements for these two operations and the following axioms. First, we have commutativity and associativity of plus operation, some axioms for natural elements, associativity of multiplication operations, and distributivity. But why we talk about semirings, why these axioms are natural for any path problem? Let's see. First, start with associativity and commutativity of plus operation. What the semantics of the plus operation in the algebraic path problems? The plus operation aggregates the weights of a set of paths. So in any algebraic path problem, we must consider all necessary paths and compute its weights. And after that, we must aggregate this information. And in general, it's very natural that no matter in which order we consider the paths in the graph, the aggregation of this information must be the same. So here, if we first consider the set of paths in A, and second, we consider the set of paths in B, and then we aggregate this information, it must be the same if we change the order, and the same for the associativity of plus operation. Next, let's talk about associativity and non-commutativity of multiplication. What the semantics of the multiplication operation? Multiplication operation just help to compute the weight of path with given weights of its arcs. So first, let's talk about associativity. When we have the arcs on one path, it's no matter in which order we compute these multiplications from left to right, and the resulting weight of the path must be the same in almost all path problems. But about commutativity, it's not true, because in some applications we may need to preserve the order of the edges on the path. So if we have a commutativity on multiplication operation, then the reversing the reordering arcs in the path will not affect on the weights on the paths, but it's in general must be not true. And also about semantics of distributivity of multiplication operation over addition. Here it's more about optimization of computations, because this distributivity helps when we aggregating paths with overlapping edges. Let's see, if we have two paths AC and BC with overlapping edge C, then this distributivity helps us just optimize the computations, and this is important because the number of paths can exponentially grow, and without this optimization, some algorithm can really suffer. And the same about the other distributivity axiom. And as I said before, we have some additional elements, the element for empty path and the natural element 0 for that describes the situation when no paths found. But this is a classical algebraic structure for this path problems, but we also have some may have some additional properties, or we don't have some axioms from our semiring definition, and let's see what it means. If we also on semiring have a canonical order, so this if some order satisfies this rule, then we can talk about uniqueness of the solution. We just get the minimal solution with respect to this order. And this such semirings called here dioid, and we can see that semiring is dioid, for example, if you have idempotent plus of plus operation, then it also bounded semilattice. And also your semiring will be dioid if you choose the plus operation as a selective operation when a plus b equal to a or a plus b equal to b. So select one of two. And here we can talk about uniqueness of the solution, but also the important semirings with elements which has the elements in carrier set, the sets of paths or sets of information about paths, path weights. And here we we already see in example with finite state automaton. Here we have can have usually plus operation defined as just union of these sets, and it's already will be ordered by set inclusion. And other optimization which also can be if we have a finite set, then adjacency matrices that we used can be decomposed to Boolean matrices. Also, the associativity of multiplication operation is one of the axioms in semiring, but for some path problems and applications, we may not have this associativity, and what it means. For example, some algorithms or some optimizations are now cannot be used for such algebraic structures. For example, when we compute when we solve some matrix equation, such optimization as block decomposition cannot be used if you don't have associativity in for multiplication operation in your algebraic structure. And if you have some problem and you try to build the algebraic structure for it to solve it like a path problem, then you can build some algebraic structure without some of axioms like distributivity or multiplication associativity or both. And then there's some ways how you can extend the carrier set S and add to this elements additional information and build the semiring on such set and solve the initial problem with all these properties. And now we can look at how the algebraic path problem in general looks like. If, for example, we have associativity of multiplication operation, then we just want to compute the weights of paths in the graph, which are just the product of weights of its arcs, and then we just want to compute for each source vertex I and destination vertex j the following sum of the weights of paths between these two vertices. And in this formulation, the problem is called the algebraic path problem. And now let's talk about solutions. There are a lot of solutions, and almost all of them uses matrices. And let's talk about matrices first. When we build a semiring, we can define the operation over the square matrices like as usual, and if we do so, we get another semiring for these matrices and defined matrix operations with zero natural element as a zero matrix and natural element 1 as a unit matrix. And then we can formulate our problems as a matrix equation. And here we again use the splitting of the paths into two parts. First is first arc and the rest of the path. But also we can use a symmetric variation of this equation where we split paths using the last arc of this paths. And we want to compute the solution of these equations, and the closure of matrix A is a solution. And let's give some conditions for existence of this solution. This condition, if one of these conditions holds, then we have the convergence to A star within a finite number of steps. and it just guarantees that after traversing each cycle in the graph enough times, the sum will no longer be changed. First condition, if for every cycle C, weight of this cycle plus 1 is equal to 1. Then we just have the limit reached at some power of A less than number of vertices in the graph. The second condition is if multiplication is commutative and each cycle in the graph is p-stable, then we also have the convergence. And the last condition is if the set of all entries of matrix A is P nilpotent. That means that the product of any number of elements greater than P will be 0. And then we also have reach the limit. And here we can see that our existence of the solution depends on the algebraic structure and of the cycles in our graphs. Also, in general, the solution of such matrix equation is not unique, but for example, if we have a dioid with canonical order, then the solution A star just is a minimal solution with respect to this order. And for almost all applications, we have such algebraic structure as dioids, and then we have the uniqueness of the solution. We can look at many solution procedures. Just let's see some classical ones. First is simple repeated squaring. We just, if we have idempotentity of plus operation, we just can repeatedly squaring the matrix I plus A and get and compute the A star, but only if we know that we can do it in finite number of iterations. And if, for example, we know that k iterations is enough, then we must square matrix logarithm times. Another example from algebra is just elimination Gauss-Jordan elimination algorithm. We just use successive elimination of variables from our system of equations, and on each step we have to be able to compute the closures of the semiring elements. Here you can see we compute the closure of the element and update other elements. And it's interesting that exactly the same algorithm is just Floyd-Warshall algorithm from graph theory. We just have the same lines here. And let me give you some intuition about this. In all algebraic path problem, we just consider the set of all necessary paths and compute its weights. So how we will explore our graph and consider different paths. We will split our set of all possible paths into such classes P, I, J, K, and this denotes the set of paths from I to J whose intermediate vertices belong to the set from 1 to K. And empty path, for example, assumed to be contained in such class. And we just use the elimination algorithm, and on each iteration we consider only paths from such set with iteration number k. And how we do it? We just consider all. We already consider all paths from previous class, and we try to divide in every possible way the paths from this class into subpaths from already computed class. So here we have also the graphical interpretation, and our elimination algorithm can be looked just as algorithm with vertex elimination. We just on iteration k consider the vertex with this number and try to remove it. And we just want to handle all the paths that will be lost after removal of this vertex. And we find the incoming and outgoing arcs with this vertex, and add the shortcut arcs with new information on it. So we must compute the necessary transitive, the necessary closure of the element, and multiply it to other two weights of the arcs. And here we eliminate the vertex and have some new arcs with complex weights. Another classical algorithm that also can be viewed as generalized by semiring algorithms, just Bellman-Ford, and here we can see how short it is. We use the plus operation for vectors and multiplication, vector matrix multiplication. And for this algorithm, we don't need both left and right distributivity. Only one is required. And for example, if you want to solve not a single source shortest path problem, but all pair shortest path problem, we can do it using a different matrix equation. And also the well-known algorithm of Dijkstra. Here we have the next the following condition. Our structure must be semiring, must be selective dioid with largest element natural by multiplication, and the condition for this element being the largest element is equivalent to the condition for non-negativity of edges in the classical algorithm of Dijkstra. And many algorithms for different problems can be reformulated in terms of algebraic structures like semirings, but there are also interesting theoretical properties of it. Sometimes we can have the same complexity as canonical complexity, but sometimes the best known linear algebra based algorithm has worse complexity than canonical one. But in some cases, for example, here we have some trade-offs in complexity. But now let's talk about optimizations. The power, yes. You have a question?
Sorry, yes, Rustam, may I ask a question for the previous, for the slide? Is it right that all presented algorithms can be reformulated in terms of algebraic path problem framework?
It's depends on the author. The algebraic framework, the algebraic path problem framework must be formulated in terms of algebraic structure, like semiring, and the sum of the weights of the paths. And I don't sure about all of this algorithms, but almost all of them, yes, can be viewed as algebraic path problems.
Well, so linear algebra-based complexity is a complexity of the algorithm which which formulated in terms of algebraic path problem framework. So, for example, I can build an algorithm for single source shortest path, which has m times n complexity, time complexity. Really?
You about single source?
For example, yeah.
N square complexity?
Or m times n.
Here, Bellman-Ford.
Well, I try to explain. I'm confused with complexity less than cubic because all ways to solve system of equations has a step which equals to matrix multiplication. So it should be at least third power of n.
Yeah, yes.
How can we build an algorithm with complexity?
Yes. When we talk about system equations, it's just a direct solution, but also if we have some single source shortest path or something like this, we can look at only one column or one row of this equation in matrix format. So here we just, like in Bellman-Ford, we just not multiply, not use matrix multiplication, but use vector matrix multiplication, like this. So we can solve the whole matrix system of matrix. We can solve whole system of equations, or we can just solve the smaller one for the single source path, shortest path problem. Here we only store the vector.
Well, thank you.
Great. Now about the optimization. It's important part of this framework, because many of the solutions can be optimized in using different matrix optimizations, using different computing techniques, and for example, we consider the elimination algorithms, where we eliminate the variables from system of equation, or eliminate the vertices from the graph. So we can choose the order of this elimination, and on some graphs of special structure, we can have the very good results when we choose wisely this order. And for example, the single source shortest path problem on planar graphs can be solved in this complexity just by using special ordering of the vertex to eliminate. And for example, we have some applications in analysis of computer programs, and in this area we have usually the graphs of special structure. Usually they are reducible, and we can use it to choose wisely the order of elimination. The next optimization is block decomposition of matrix. We see a lot of algorithms that use the matrices, and we here can just use, for example, strategy to decompose the matrix into 4 blocks with square blocks on main with square blocks x11 and x22 and corresponding ones to open the possibility to apply the divide and conquer strategies and solve the smaller problems of the same type. And for example, if you for your problem you build a semiring and you have some matrix multiplication algorithm for your semiring with this complexity, then you also can have the algorithm with the same asymptotic time complexity for the algebraic path problem that solve, for example, this equation. Also, there is another decomposition optimization that uses LU decomposition. It just decompose your matrix to lower triangular matrix L and upper triangular matrix U, and solve some equations, and then the result is just multiplication of these two matrices. And also, when we implement most of these algorithms, we can use the parallel computations and sparse matrix representations. Now let's talk about applications. We have a lot of applications for this framework. For example, the different optimal path problems like shortest path, k-best paths, lexicographic optimal paths, but also some application in network analysis, social networks, in analysis of the program, where we just want to know is some variable was changed or not in some part of the program. And in network analysis, we, for example, can solve the problems like reliability of networks, the reachability of one node in network to another, and so on. And a lot of graph theoretic problems which not use directly the paths. For example, we don't want to find some paths. We want to testing the biparity of a graph, or finding the bridges and the cut vertices of a graph. And for example, this problem of finding bridges and cut vertices is also related to network analysis, because these bridges and cut vertices are some important or weak points in the network. And also many problems which uses formal languages. We see the problem of constructing regular language by the given finite state automaton. Also, we can avoid the infinity of this language by constructing the regular expression by the given automaton. Also, here is our algorithm for context-free path clearing, where for given context-free grammar we want to enter graph, we want to find all paths in the graph that satisfy this context-free grammar, and this is a part of my dissertation. Some algorithms are also are algebraic path problems, and there are a lot of application and semirings for this applications. Here, for example, we can see if we want to find shortest path in weighted graph, we use such a carrying set and min plus operations. But we can use the same solution procedures, but just change the carrying set and the operations to max and plus. And we already can solve the different problem. For example, also these problems related to network analysis, reachability problem under deterministic edge failures. It means that you know that edge either exist or not, and you want to compute the reachability between the nodes of a network. It just uses the Boolean semiring. So here we use max and minimum, but it can be the disjunction and conjunction operation for logical variables, logical values. And also in networks, as I said before, we can find the bridge and cut vertices by using such interesting semirings. We will talk about it next. And in more general problem, we can have not deterministic edge failures, but probabilistic edge failures. We can have for each edge between two nodes the probability of failure of this connection. And here we can use this complex semiring and use the classical algorithms to solve this problem. Yes, and again, the many applications for different social and network analysis. And about finding the bridges and cut vertices. Some algorithms can reuse the classical algorithms, but they will not have the good complexity. For example, if we want to find all bridges and cut vertices, this is just the edges. By removing those, we will increase the number of connected components, and the same cut vertices will, by removal of cut vertices, we will have we will disconnect. We will have disconnection in some connected component. And these problems can be solved by using correspondingly these two semirings with sets of edges as a carrier set, and just intersection and union operations over these sets. We initialize the matrix A just by sets with one existing edge between these two vertices, and we want to compute the set of edges that belongs to every path from I to G. And if, of course, we have except this edge some other edges in the end of computations, then these edges are bridged. And the finding cut vertices are the same, but we just initialize it with vertices and try to intersect and union the set of vertices. And for example, if we use just repeated squaring, we get the complexity is logarithm of size of the number of vertices and on the complexity of multiplication, matrix multiplication of two matrices of the size of the number of vertices, and in our such semiring, and this is not good enough because the canonical algorithm, for example, is linear. But such algorithm may have some good implementation using sparse matrix representation and parallel computations. And also, let's look at the again at the finite state automaton, but we now want not to determine the language, but we want to describe it by constructing the regular expression, and this can be done very easily. We already see this figure. We just can eliminate some vertices, and when we want to add new arc with computed difficult weight, we not compute the closure of the element, but just add the star symbol for this value, and we will have at the end on the arcs the regular expressions, and we can have the finite representation of maybe infinite set of words here. And in conclusion, I want to say that the algebraic path problems can be applied for many problems in different areas. It's really easy to reuse many of canonical algorithms by just using different semirings or other algebraic structure, and these algorithms are different. We can solve the system of equations. We can work with matrices. We can building up the infinite sum of path weights. But from practical point of view, we have a lot of optimizations that can be applied to these algorithms. For example, we can compute matrix. We can compute matrix operations in parallel and use the sparse matrix representation, and get a very efficient implementation of these algorithms. Thank you. I'm glad to answer your question.
Thank you, Rustam. Does anybody have any questions?
So I have a question, but the first question is more practical. So you mentioned that these ideas are used in the graph BLAS, right?
Yes.
And so the idea is that you in graph BLAS you can write your algorithm in terms of this. Essentially, you can write your algorithm as some expression in a semiring syntax, right?
Yes, but semiring, we construct semiring for the elements of the matrices, and then we can, in a natural way, define the matrix operations over the semirings. And if you formulate your algorithm in terms of this matrix operations, then yes, you can use GraphBLAS for parallel sparse implementation.
Yeah, but I wonder how do you write these algorithms in GraphBLAS? It's just like a bunch of call bunch of C functions or what?
If there are different GraphBLAS implementations, for example, we use suite sparse C library, and we just have, let's look at, for example, Bellman-Ford. We just write in pretty the same way as here, on different languages we can write. We just define we just choose the semiring that we want to use. It can be one of the built-in semirings in the GraphBLAS, or the possibility of making your own user-defined semiring, and you just can create an object called semiring by putting the two operations, plus and multiplication, by putting the carrier set and the natural element, and using this, and you have the function of multiplication of and addition of matrices and vectors that have that has an argument, the semiring. So you just put in this call your semiring, and the same operation, matrix multiplication, for example, will be computed according to given semiring.
Okay. Yep. Let me just explain why I'm asking this. I'm asking this because, so, like looking at how it looks, yes, on paper at least, I can imagine that if you write this algorithm in terms of this semiring algebra, yes, then I can imagine some like optimizing compiler that would look at these expressions and try to rewrite them using this rules, axioms of the semiring, to like and to try to construct like an optimal program for your for what you have written.
First, let me notice that semirings in implementation, especially in GraphBLAS, is not really theoretical semiring. So it's we don't have all of these axioms here in explicit way, and we just can define our semiring by putting the arbitrary function or over the two elements. For example, for defining the semiring, we must define the plus and multiplication operations, and in GraphBLAS it just two arbitrary, almost arbitrary functions, operators, and there are no axioms, and when we implement when we write some algorithm in GraphBlast, it just it will call many times this function defined by us, this plus function, and give
Yes,
algorithm.
yeah, I understand that you probably cannot if you write this in C, you cannot like prove that your the functions that you pass are satisfy these axioms. But I assume I think that GraphBlast actually assumes that these operations that you pass to the library satisfy all the axioms.
Mm-hmm.
Yeah.
Yes, this is difficult.
More questions?
Yes. I see that Semyon sent some paper.
But maybe some of the optimization can be. I just don't see it in GraphBlast main papers. Maybe.
So, Evgeny, if I understand you correctly, so yes, you are right. We can just build a rewriting system which can use some axioms to optimize code. It may be difficult to do it for C implementation, obviously, but for some model language, or why not?
Yeah, actually, like related question. I just wonder, is this given this some semiring and some cost model, like we assign for each operation some cost, and can we find an optimal expression? Like, can we make this?
I guess yes, and I guess that we will have a discussion with one of authors of this paper. So I hope that we can, but I don't know how to do it exactly.
I see. It's interesting.
So yeah, one of possible way is to use distillation, for example, or something else. I don't know, but we try to do it. We try to use supercompilation and distillation for such code optimizations. And I think that it is a very interesting direction because manual optimization of C code is a very difficult task.
Yes, but are you doing this in C or F sharp? I think in F sharp you
Haskell.
can have. Okay, in Haskell you can have like a nice DSL for this and like perform optimizations on this DSL.
Yeah, that's why we choose Haskell, not C.
Yeah, cool.
More questions? Actually, I have one. Maybe I have two. The first one is it's always a good thing to have a new view on a set of problems, a set of seemingly disconnected problems, which can be covered by a single framework. So we can go right. But my question is, what is the performance impact of using these common formulations? So if you can compare the same task being solved with this generic approach, with the specialized algorithm, what performance impact would it have?
Yes, thank you for the question. Firstly, for some problems, maybe some researchers have tried to find the algorithm because there is no algorithm yet for this problem, and this approach can help to find the first algorithm. And the Second, that I said about practical point of view, the canonical algorithm can have the same complexity, the same theoretical complexity, but here, if we get an algorithm and put the almost all complexity into the matrix and vectors operations, we can get the most efficient implementations, because there's a lot of optimizations for such operations. And classical algorithms can be maybe implemented very slow.
So generalizing might have a positive impact. Might make algorithm faster.
Can you repeat, please?
I am saying that I understood your answer as these generic implementations can be faster than canonical algorithms.
Yes, yes.
Wow.
In implementation, for example, yes.
Yeah, I see. And my second question is, do you know if A-star algorithm can be reformulated in these terms? Because it's quite closely related to shortest path.
Sorry. Can you repeat, please, the question? The first part of the question, I don't hear.
Yeah, I was asking if A-star algorithm, the heuristic search for shortest, like the shortest path, can be formulated in these terms.
Sorry, which algorithm of shortest path?
Yeah. I just saw it on the previous. Yes, try to yes.
Here, yes, here.
No.
It's not
well, the denotation is exactly the same. A star, A power star. But this is a specific algorithm of heuristic search, which is extensively used in artificial intelligence, or it used to be used in artificial intelligence until that word was taken by the ML people. So it's a heuristic search for which can be formulated as a finding at a path with the shortest distance. But it has some nice properties and use it in many to solving many search problems. So it's looking like similar to those problems you already mentioned. So I'm wondering if A star can be reformulated in these terms.
A star problem, I think yes. A star can be reformulated in these terms.
Well, cool.
Yeah, it's because it's very similar to the Dijkstra. Just Dijkstra plus
yes,
you just change the weights function. You add
yes,
this.
generalization of Dijkstra. Yes. Any other questions? Nope. Well, then thank you, our presenter, for the talk. Very interesting, and see you all on the next seminar. Bye bye.
Thank you.